Hello everyone, I'm Quentin Jullien, Fire Protection Engineer from CSTB, the Scientific and Technical Center for Building in France. Today I'm presenting the continuation of a work initiated in 2019 on evacuation modeling, and it focuses on benchmark analysis of input parameter, sensitivity of software simulation. For the content of this presentation, I will begin with the context, then with the experiment setup, before presenting the sensitivity analysis and the conclusions drawn from it. First of all, the context, global as well as national, concerning the French regulation. Complexity of modern infrastructures, size of crowds, aging of population or disabilities raises new issues and so a need for new tools. However, there is no international standard. There are guidelines in different countries, like ECFP handbook in France. However, regulations are mainly prescriptive. The use of simulation tools in France is restricted to specific fire engineering aspects, such as assessing fire performance of smoke ventilation systems or performing structural calculations. Furthermore, evacuation modeling is not yet acknowledged in the building sector, likely influenced by the absence of a performance-based requirement. However, managing crowds, especially during major events, is increasingly challenging for public safety in the current context, given the scale and complexity of the situations faced. Especially now because France is preparing to host several major events, such as the Rugby World Cup 2023 and the Olympic Games 2024. Changes to the French regulatory structure regarding evacuation may now be necessary and inevitable to allow new innovative designs. The research presented today has been carried out in collaboration with several partners presented here, by 7 French institutions on a UK-based consultancy in a project called EVAC 2024. The consortium also includes firefighters. Goals of this collaboration is to make an inventory of models that can be reasonably used to estimate crowd movements in various situations, with or without crisis, in or out of buildings, etc. Select appropriate input parameters common across most of the evacuation models and tools available to study the impact on the egress time. And build an analysis methodology that would allow to conduct meaningful comparison between the chosen models. As mentioned before, this work is a continuation of a previous work, where dispersion of results was observed between different software within the same application case, evacuation of an office building, and despite having the same common parameters and with tool-specific parameters being set to default. At the time, conclusions have pointed at the congestion management in the different tools. Thus, the objectives of the study are to conduct a sensitivity analysis on 3 common input parameters: speed, agent size, and pre-movement time, using 4 different egress models. 2 kinds of analysis were used: general sensitivity study analysis and Sobol's indices analysis. I will explain later the specificities of Sobol's indices, and to study the influence of these parameters on congestion and hence the egress time. Let me present the experiment setup first. We have observed an evacuation drill of an office building at the end of the year 2019. It was a 9-story office building in Paris. You can see on the left a schematic view of the building, and on the right, geometric characteristic of the building and the distribution of the occupant the day of the drill. The occupants were 1,349 persons, which represents around 40% of the total capacity of the building. The 2 figures on the right describe schematic views of a common level for the one above and of the ground floor for the overview. As mentioned in the previous slide, there are 8 egress stairs. We were 20 members on site to record data such as pre-movement time of the occupants before to evacuate with them. It allowed us to measure the time required to get down the stairs and evacuate the building. 3 cameras are installed in stair C. The one at the top right because it was deemed to be the busiest stair as per building operators' experience. There is also CCTV network in common areas. The assembly point is in a little park at the right of the building. And in terms of performance, time to evacuate the building was of 7 minutes and to reach the assembly point, 8.5 minutes. Now let's get to the sensitivity study. 4 tools were used for the sensitivity study: PathFinder, building EXODUS, FDS+EVAC, and Cromosim, the compartment model. 3 of them are microscopic models, and one is a macroscopic model, Cromosim. At this point, we can already observe differences between tools in terms of representation of space and occupants. It implies inevitable discrepancies in the calculation of congestions and conflict resolutions. Indeed, a triangular mesh, a fixed square mesh, a rectangular mesh, and a network are intrinsically different. The same goes for using a cylinder, a square, an ellipsis, or macroscopic discretization as an agent representation. It appears important to take into account, if it is possible, a main and universal parameter for the sensitivity study. I said if it is possible, because the diameter of a person, or agent size, is not a parameter for building EXODUS. An interval of pre-movement time is not applicable to a macroscopic model. The quad can only have 1 pre-movement time, which leads to an offset basically. Changes of agent size in Cromosim are done by modifying the capacity of the doors. And so the parameters are selected for the study are velocity, agent size, and pre-movement time as described in the table. These values are representative of those found in literature and user guides of these tools. The different tools are more or less stochastic. It implies a phenomenon that we call intrinsic variability. To avoid this variation impairing the results, it is necessary to perform a certain number of simulations, different for each tool, and use the mean value, which shows a standard deviation of 2% with a confidence interval of 95% as a criteria. Under this standard deviation, the mean value is considered stabilized. The sensitivity study. First, general sensitivity analysis. Let's begin with individual impact of variables on total evacuation time. On the first one is the speed. This graph presents evacuation time variation versus speed variation, both in percentage for the 4 tools. 2 global trends can be observed, almost linear, and magnitude varies between tools, and discrepancies are due to the difference in management of staircases, door, and interactions. Indeed, algorithms are different. Slope is steeper for the lower speeds. It can be explained by the presence of congestion that disrupts the evacuation. Indeed, the higher the occupant speed is, the sooner they arrive at the bottlenecks or the landings here. Then more occupants find themselves in the stairwell at the same time, hindering the otherwise smooth movement. Evacuation is therefore governed not so much by the occupant speed itself, but by the congestion that limits it. Then let's focus on the agent size. As mentioned before, agent size is not a parameter for building EXODUS. It can be observed that the sensitivity is low for small diameters. This is due to the flow of agents through doors being at or near maximum capacity. In Cromosim, conflicts are managed differently, so the sensitivity to agent diameter is low. For FDS+EVAC and PathFinder, high sensitivity for larger diameters, 0.5 meter to 0.6 meter, is observed. This is due to higher space requirements. Doors and stairs leading to lower flow rates and lower evacuation times. Increase in agent size generates congestion in the stair. The first view, the one above, you can see The evacuation in PathFinder at 250 seconds, floor 6, staircase A. And on the overview, at the same time, but for a diameter of 0.4 meter, there are still occupants still queuing in the staircase. After speed on agent side, the pre-movement time. As I said before, applying an interval of pre-movement time is not possible in Cromosim due to a macroscopic aspect. It can be observed that the sensitivity is low, around 5%, and it is the maximum for the interval from 0 to 60 seconds. It can be observed, this is because the egress time in the building is largely governed by the flow in the stairs, which represent the bottleneck of the system. Indeed, even if occupants are delayed before starting the evacuation, they will eventually reach a stair that is already jammed. After the results of general sensitivity analysis, let's continue with Sobol's sensitivity indices. During this presentation, I won't be explaining the details of the statistical analysis method. But to quickly present Sobol indices, I can say that you can take into account the number of input parameters you want. Here it's speed, pre-movement time, and agent size. Then by providing a value for the different combinations of input parameters, the mathematical model returns an output that quantifies the influence of each input parameter based on variance analysis. The main advantage of Sobol indices is to bring a quantitative information on the influence of a parameter on the weight of cross interactions between 0 and 100%. However, we have limited ourselves to study only a few couples of parameters. Indeed, the number of calculations increases rapidly and leads to an excessive amount of calculation time for some tools. This graph presents the influence of speed, agent size, and their interaction. It can be observed that different tools react in the same manner. Variation is predominantly due to speed, near 80%, and variation due to agent size are from 14% to 22%, depending on the tool. The less than 5% remaining correspond to the variation due to cross-interaction between speed and agent size. They are therefore here independent in the case studied. Then this graph presents influence of speed, pre-movement time, and interaction between both. Influence of speed is clearly predominant, with over 90% of the sensitivity. In PathFinder, the effect of pre-movement time on its interactions with PIV is negligible. Speed influence is ultra-predominant with near 99%. Finally, speed and pre-movement time are independent variables as well. And last but not least, conclusions and perspectives. As expected, speed is the main parameter in terms of influence, as we've seen from the general sensitivity study, as well as when compared to agent size or pre-movement time through Sobol indices. And congestion limits the egress time for higher speeds. And micromodels are much more sensitive to size variation than macromodels. Pre-movement time influence is negligible in the interval considered because congestion seems to outweigh the delay of pre-movement time. Same trends are observed for the different tools studied. Obviously, differences in amplitude between results incoming from the different tools are seen, typically at doors on merging points, for example, the staircases. This raises a practical question about how the priority of access to the stairs is managed, and whether people coming from higher stories impede evacuation of lower stories. Additionally, the different solution of conflict resolution implemented in the tools may affect the merging of the throws. Those different results highlight that quantification of congestion and knowledge of conflict resolution is crucial. Furthermore, these results are valid for the intervals and the case studied. Indeed, geometry and the number of people influence the results, such as the length of the interval considered. And concerning the avenues for future research, special attention should be paid to the modeling of the stairwells or other bottlenecks, The way the space is discretized, I can only modify the results through the conflict resolution algorithm, which are different for each tool. This work confirms the interest of studying congestions, and not only the evacuation time as a final result. Indicators as PEE, personal egress efficiency, which can be described by the complementary of the ratio between the individual waiting time and the personal evacuation time. And more simply, we can use the individual waiting time. Finally, as I said before, the results are heavily linked to the case studied. Other drills are needed to make comparisons and extend and confirm the conclusions. And because things are getting back to normal, regarding COVID restrictions, or at least I hope so, we will be able to conduct another evacuation drill this year on a different building with another type of population. And I take the opportunity to thank the building hosts for their hospitality and the fire brigade officer, Paris Fire Brigade and the Juras Fire Brigade for their help during the drill. And thank you, Anastasia Burden, for your help to make this presentation. Thank you for your attention.
Thank you. Questions in the room?
It's more like two comments, really. But for the upcoming drills, I was wondering whether it's worth you sharing almost like what inputs you need, because it may be there are drills going on that people collect data on that they could just share it with you, because you want those data sets, right? You need those data sets to continue the process, especially looking at a drill where congestion doesn't dominate. I guess that's what you really want, right? Which is a different case.
Yes. It will be in a university.
Oh, you've actually got one lined up. Okay.
For the next drill. And so the population is different.
Yeah.
More young. For evacuation, it will be easier. Because in this office building, occupants take the same staircase to go outside, not all the staircases. And so there is congestion.
Just got one follow-up. Okay. So the other thing I was thinking of is with the EXODUS model, because it's a nodal grid, a uniform nodal grid.
Yes.
You could reduce the size of the arcs between the nodes, right? And so you effectively reduce the size of the people, but the problem is it's uniform.
Yes.
So you just lose a lot of the variations straight off. But I guess it's worth, because it's a general problem, right? It's not just any model that uses a nodal grid like that. You could reduce the size of the people, but it's sort of redundant because you're changing the shape of the space effectively.
Yes.
So it might be worth just discussing that when you present it, because it's actually quite a significant issue.
There is also a question with doors. In France, we have a concept used passage unit for a door of 0.9 meter. It's 1 unit passage. 1.4 meter is 2 unit passage. And in building EXODUS, we have the choice to connect some arcs to cheat on the number of the number of passageway. Yes.
Okay. Hello, thank you for the presentation. I just have a question regarding the sensitivity analysis, because the model you introduced has some inherent stochasticity inside the uniform distribution. That means for one point in the parametric space, you can obtain different trajectories of the model. So multiple evacuation times. Have you somehow encountered or solved this within the sensitivity analysis? Was this run multiple times or just one simulation for one point in the parametric space?
We realize it depends on the tool studied. For building EXODUS, 20 simulation for each point of the sensitivity study. And I think it's the same thing more or less for the other tools.
Okay, so yeah, it's perfect. And then for the sensitivity analysis tool, you have used the average of those 20 simulations or all the
average.
The average. Okay, thank you very much.
You had very small pre-evacuation times, also 15 seconds, 30 seconds. Is this normal for the French population in office buildings, for example? Because we would use a lot longer.
During the evacuation drill, we record up to 2 minutes.
Okay.
The mean value is near 60 seconds. So we test 0 to 60.
Great, thank you.
Okay, thank you very much.